A lot of these uninitialized variables are pretty hard to exploit if you don't have good control over the contents of the heap. For example, in the use after free case, you need to be able to take the block that had just been freed and allocate it, fill it with your own custom data, perhaps free it again. So the heap manipulations that are required there are more complicated, and this is what prompted this research. The final thing that you can attack is the application data on the heap. Since you can no longer use the heap headers, you can use the data that's after them, which would be specific to the particular application and the particular code that uses it. Maybe you have an application-specific memory allocator that still uses a doubly linked list that's not protected by the safe unlinking feature. Maybe you have function pointers somewhere on the heap that you can override. Maybe you have C++ object pointers. The difficulty there is that because the heap is so dynamic, you don't really know what data is located after the buffer that you're overriding. But with Heap Feng Shui, you can make sure that the data located there is the data you want. So you'll find out how in a little bit. Let's look at one of the exploits that came out last year. It's the WebView set slice exploit. And it was added to the Metasploit framework. And it worked pretty well in most cases, except that it relied mostly on random luck. So in some cases it would work, in others it won't. The set slice exploit was a buffer overflow where the buffer was underflown, so the data before your buffer was overwritten. What the Metasploit exploit did was fill the entire heap, fill a large chunk of the heap with shellcode. This is called heap spraying. And then trigger the vulnerability repeatedly in a loop, overriding random pieces of data on the heap with pretty much random pointers. And hopefully, if you're lucky, one of these pointers, the data that you overrode would be a function pointer on an object pointer, and calling that function pointer would get shellcode execution through all the shellcode that you've placed on the heap. In most cases, it actually worked. I was very surprised. It did work pretty well, but it was not 100% reliable. So I was trying to improve upon this exploit. But before we get to that, let's talk about heap spraying for a little bit. So you're probably mostly familiar with heap spraying, but here's a very quick overview. It's been used in almost all exploits, Internet Explorer and other browser exploits since 2004. It relies on the fact that JavaScript strings are actually stored in the normal heap area, and they're not really modified in any way. So you can build a string that contains the bytes of your shellcode preceded by a long no-op sled, and you can fill the heap with this string. It's not always necessary to fill the entire heap. You can only do 200 megs like the code that's shown there. Here's how this looks in the actual memory address space. So this would be the heap of Internet Explorer. We have a few allocated blocks shown in blue down on the bottom. There is some fragmentation, so there are some blocks that have been freed, so we have some free holes there. And then after that, we have a lot of empty space that hasn't been used yet. After we do the heap spraying, and after we allocate 200 megabytes of these strings that contain the shellcode, we're going to have the green area there filled with our shellcode. And it'll fill out all the holes caused by the fragmentation, and then it'll fill out the rest of the memory. So if you have a memory layout like this, then jumping to an address that's somewhere inside the green area will get you shellcode execution, because the green area contains a lot of copies of the shellcode, one after another. One address that's commonly used is the 0C0C0C0C address, and I'll go into that in a little bit. I'll explain why this particular value has some interesting properties for us. But what you need to take from this slide is that jumping anywhere inside the green area will lead to shellcode execution. So if you can override a function pointer after you have done your heap spraying, and the program calls that function pointer, the function pointer will contain that address that you put there, 0C, 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 which is inside the green area. And then the program will jump there, and it will land on your knob slide. It will execute it, and then it will reach the shellcode. So you're done. A more interesting exploitation technique is using this to exploit object pointer overrides. Now, object pointers in programs compiled with Visual C++ point to the object data, and the first 4 bytes of this object data contain a pointer to a vtable. The vtable contains function pointers for all virtual functions for this class, for the C++ class. So if we overwrite, so to exploit this, we need to spray the heap with 200 megabytes of shellcode, but as a knob slide, instead of the standard OX90 byte, we will use byte C, which is a valid x86 instruction. It's, for all practical purposes, equivalent to knob. We don't care about its effects. And it is also a 1-byte instruction, so it works well as a knob slide. We will override, so we will fill the heap with this OC knob slide followed by shellcode, and then we'll override a function pointer with the OC value. Then we will wait for the program to call a virtual function of this object. When this happens, the program will treat the data located at address OC as a turn this off. It will treat the data located there as a fake object data. The first 4 bytes of this fake object will be the vtable pointer. But because we've filled the heap with this OC byte, the vtable pointer will also point to the same address, 0C, 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 0C. So now the program will use the same data, but it will use it as a vtable. Let's say that we're calling virtual function at offset 4. The program will read that data there, and that data is, again, 0C, 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 because this is the byte that we filled the heap with. The program will use this as a virtual function address, and it will jump to our code located at 0C, 0C, 0C. Again, the bytes there are 0C, 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 but this byte is also an executable x86 instruction that we're using as a knob slide. So the program will execute these bytes and eventually reach the shellcode. Again, this is the standard technique used in a lot of exploits since 2004, but we will see how we can improve upon this. The problem with the set slice exploit is that it is HD, but it is often unreliable. If you're lucky, it'll work. So if you're going for mass exploitation, maybe it's good enough. You'll still get 50% of your targets. But if you're trying to do more directed, targeted attacks and you need high reliability, you need something better. The problem is that when you overwrite application data, you need to know exactly what the heap layout is. For example, for the set slice exploit, we were overwriting the block located right before us. If we could be certain that this block contained function pointers and object pointers, then we would have guaranteed 100% reliable exploitation. So what we need is to control the heap state of the application. And this is what I call Heap Feng Shui. The heap allocator behaves deterministically. It's a very important property for our purposes. It means that if you do the same sequence of allocations, you'll always get the same result. Also, the blocks are mostly allocated in sequence. So if you start with an empty heap and allocate 2 blocks, which are shown there in blue, these 2 blocks will be located right next to each other. The first one will be in the beginning of the heap, the second will be after this. So we can use specific sequences of allocations to force the heap to have a specific layout. For example, if we start with a heap that looks like this, like the slide there, and we allocate two 4 kilobyte blocks. They will be allocated, again, right next to each other. They're shown in orange on the slide. Then we will free the first block. We will free the first piece of data. So now we'll have this free block, but it will still contain the data that we put there originally because it hasn't been reused. Now, let's say that we trigger some kind of, we use an ActiveX object or just some other component of Internet Explorer that allocates a 4 kilobyte block. The heap allocator in this case will get the block from the free list, but the only thing on the free list is the block that we just freed, which means that the application will receive the same block that we freed that has been filled with the data that we put there. If that component, if that code has an uninitialized data bug, which means that it uses the data there without actually writing to it first, it will use the data that we put there, the values that we put there. So if we can use this to control a function pointer or an object pointer, we can apply the techniques that I described in the previous couple of slides and get shellcode execution. So this is the crux of the Heap Feng Shui technique. Like, this is the most important piece of the presentation. Everything else is just implementation, technical details. But this demonstration here shows that if you do the allocations in the right order, and if you know what kind of allocations the application will do, you can influence where the application data will be located on the heap. So if we do this and the application is vulnerable, we just exploited an initialized data bug. So we want to do this in Internet Explorer, and we're going to use JavaScript to do it. Heap Feng already proves that JavaScript strings go on the standard Windows heap without being modified in any way. So it proves that we can allocate data on the heap that a lot of other pieces of Internet Explorer use. We also know that we control the data inside these blocks because that data is the strings that we put there. Now, if we have a way to allocate these blocks of a specific size, let's say you want to allocate a 256 byte block. If we have a way to do this, and if we have a way to free specific blocks, then we would be able to use the Heap Feng Shui technique to control the heap state. But to do this, we need to look at how Internet Explorer actually uses the heap. So in this part, we're going to talk about the internals of Internet Explorer. There are three main components of Internet Explorer that are relevant to our exploitation efforts. Those are the JavaScript runtime engine, which most of its code is located in jscript.dll. The MS-HTML rendering engine, which is responsible for rendering HTML. It's located in MS-HTML.dll. And ActiveX objects, which are located in whatever DLL you're using, depending on the specific ActiveX object. I've put ActiveX objects here because a lot of the vulnerabilities over the past 2 years, which prompted the development of these techniques, were actually